Hey scholars, so I was thinking of doing this as an infomercial, so why not? Does this ever happen to you? Alright, I'm done doing that. Anyway, what I want to talk about today is objects that have friction between them and the surface they're sitting on. But we're going to get things a little crazy here. We're going to go at an angle. So check this out. I'm going to play a quick video here. I have two different sort of old phones just lying around, and I've noticed this in the past that some phone cases are really slippy and others kind of grip the surface, less likely they're going to fall off when you don't want to. So let's actually talk about how we can analyze some of that a little bit. So take a look at the video here. So what I'm doing is I've got a protractor here, and this isn't super precise, but we're really just trying to give you the generic idea. So I'm going to lift this up, and what we're going to see is that this phone compared to a different one, they're going to fall at different angles of inclination. So check it out. Okay, so this one, did you notice it just started the slide? I'll play the video in a moment. It's right around 15 degrees, okay? I would call this the slippier of the two phones, just from like my subjective experience. So let's take a look at the second one. We lift it there and we're at, much higher. It just starts to slide right at about 30 degrees. So it is completely a coincidence that this one went twice as high, 15 degrees, this one's 30 degrees. But what we want to look at is if we can determine the coefficient of static friction or do any kind of analysis just based on sort of where this thing falls. And the kind of crazy thing here is that you can. All you need to know is what angle does this begin to slip at. That's actually a way you can work backwards and find the coefficient of static friction. So let's jump into that analysis. We're going to take some quick notes. If you don't already, take out your notebook, please. Even though our picture has it going the other way, I prefer to draw my inclines like this because I'm right-handed. Either way. So we want to draw this pretty big so we've got plenty of space for our analysis. And we've got our block sitting here on the inclined plane, and our basic scheme here is we're going to increase that angle theta until we get it to just start to move. So this is really critical, actually. So we're still going to say that the acceleration is 0. This is the moment before the block starts to slide. So the idea here is that we're going to reach sort of a critical angle as we increase the angle at the moment that we reach this theta, whatever specific one it is, the thing will start to slide. So from there we can do our analysis. And I'm going to break one of the rules that we've been doing, which is I'm going to draw on our picture just a little bit. It's going to make life easier for us here. It's kind of weird, but what we're going to do to analyze this, turns out angles make things kind of awful unless we do one smart thing. What we're going to do is we're going to rotate our coordinates so that instead of x and y being like this and like this, you know, the standard x and y, we're going to make it so that the plane here is the xy plane. So let me show you what I mean. What we mean is that this part here is going to be x. So I'm going to kind of extend this out. This is going to be our x-axis, which will make up for our block like this. So all we've done is we've rotated our coordinate axis so that it matches our inclined plane. I checked with the math people, they're fine with this. This is actually a really standard thing to do in physics, to rotate our coordinate axes. Here, let me show you why this is really useful. So what's going to be weird here is now gravity is not going to act down. You're actually going to have the weight force acting at an angle relative to what up is. The reason this is going to be useful, and you'll see this in a second, is that the normal force is going to be now straight up, which is what we're hoping for. So we're going to label that N, and I need to make one quick adjustment. So I just relabeled this mg on the outside because we're going to end up breaking this into a triangle. Let me show you what I mean. So what we're going to have here is sort of a weight force that's in the y direction like this, and we're going to have a weight force that's in the x direction like this. And of course you can see we've got some triangles already showing up. You can show by similar triangles that this angle theta is the same. And then the other force that we've got here is the force of friction acting upwards. We're going to break this out into a more compelling and proper free body diagram in a moment. But what we've got is we've got a normal force and a weight force that I'm going to call mg cos theta. You can show that this is the cosine of that angle. This vertical leg there. And then you've got the one that's acting down the plane. That is going to end up being mg sine theta, because it's opposite over here, opposite over hypotenuse. So just for sake of swiftness, just accept those for right now. You can prove it to yourself that it is indeed mg cos and mg sine. But what we're going to do now is show you why this is really useful in terms of setting up our problem. So as usual, we're going to start with a free body diagram, or take the information that we have and include it in our free body diagram. We're going to do it with normal force pointing upward in our sort of unusual rotated coordinate axis here. So there's our normal force n. I've been using Fn. I'm just going to use n here because I got lazy. That's totally fine. So now, instead of weight being straight down, if you look at our picture, we're actually getting sort of like one of the components of weight. As we lift that up, this triangle will be a similar triangle with the big incline. So all of that is to say that this force here is mg cos theta, and we know that those are balanced because the block isn't like moving into the inclined plane or up, it's just sitting there. So these are balanced. Now, what that means actually is that gravity in this world is sort of off at an angle like that. So this is the weight force mg. And then this little bit right here, that's our friend mg sine theta. Okay, I put it as a dot there because you can move vectors around freely. I'm actually going to move it right up here. So this one is mg sine theta. And for right now, I'm just going to scratch that out. But that's where it came from. I just moved it up there. Okay? And then the force that's opposing the weight pushing down the incline, that's what mg sine theta is. That's the weight acting down the incline. Will, of course, be our static friction force. For visual clarity, I've gotten rid of those extraneous marks that we had. All we want here are the forces in the x and in the y direction. And of course, as we've been doing, what we're going to do is translate that into Newton's second law. Okay? So what we want to do is look at the net force. That equals, of course, ma. Let's do that in the x direction first. So that's force of friction and the weight force that's going down the incline. Because it's just started to budge, we're going to say that the acceleration in that direction, let's make that really clear. So here is the y direction, here is the x direction. So that's 0, the acceleration in that direction. And all we need to do on the left-hand side is put in the forces. So we've got friction force minus mg sine theta. So we have friction force minus mg sine theta. That equals 0. So quickly solving there, we have the force of, in this case, static friction is going to be equal to mg sine theta. And we can also work this out in the y direction. So F net equals ma in the y direction. So we're going to sum up the forces in the y direction. So here that's just normal force and the weight force. Again, because this hasn't started to move yet, we can say that this acceleration in the y direction is exactly equal to 0. So F net will be the normal force up minus the weight force in our new sort of weird coordinate system. That is equal to 0. So we can move this over and say the normal force is equal to mg cos theta. Now recall from our last set of notes that the frictional force, this is on your AP equation sheet, the frictional force is equal to the coefficient of static friction times the normal force. You might have seen me write it like this. Fn is just equal to n. Those are the same thing. I'm just being lazy with my notation. Okay? So what we're going to do is where we see frictional force, instead of writing that, we can write mu s times n. So I'm just going to substitute that in. Mu s times the normal force. That equals mg sine theta. And our goal here, now we've got mu s, that's our goal. We want to solve for an equation that tells us how we can find the frictional force based on this setup. So where do we go from here? Well, what's really nice is we actually already have the normal force. So we're going to take the normal force and we're going to plug it in right here. And we're going to get something that looks like a disaster, but it's going to clean up in a very spectacular way. So check this out. So mu s times the normal force, that's mg cos theta. That equals mg sine theta. So I'm trying to solve for the coefficient of static friction, mu s, which is over here. So I'm going to divide both sides by mg cos. I should put the theta there. So this is also mg sine theta. So if we divide both sides, we have mg sine theta on the top, and we have mg cos theta on the bottom. Some of you might be way ahead of me. So we can cancel mass, we can cancel the acceleration due to gravity, and we can clean this up a little bit. We have sine theta over cosine theta. Let's remind ourselves, sine theta is opposite over hypotenuse, obviously. And if we divide that by, which we're doing here, cosine theta, which is, if I can get that right, adjacent over hypotenuse. Check this out. This is really exciting. If we do this division here, these hypotenuses cancel, and what we're left with is that sine theta over cos theta is opposite over adjacent. You might remember opposite over adjacent. Hey, that's tangent. So the beautiful thing here is our equation simplifies to this. This is, you're going to love this. So it's just tan theta. That's it. In other words, the only thing you need to know to find the coefficient of static friction is what angle does that thing start to slide at. So in a surprising way, the mass ends up not mattering. You can see right there that it canceled out. Also, a lot of folks think that the surface area might matter, but that also doesn't matter. How big my book was actually ended up not mattering, or how big my phone is ends up not mattering. So if we look back at our example a moment ago, we had that the first phone started to slide when the angle got around 15 degrees, and that the second phone started to slide when the angle got to 30 degrees. This is as easy as it gets. Check this out. So if we want to know the coefficient of friction on that first phone case, it's just tan of 15 degrees. And the coefficient of static friction on the second one is just tan of 30 degrees. Now, tangent doesn't work in a linear fashion, so it's not going to be double here. Let's actually investigate. Take out your calculator, make the calculation. Let's reconvene in just a moment. So I was careful to put my calculator into degree mode, and I found the tangent of 15 degrees is about 0.27, and the tangent for the other phone of 30 degrees was 0.58. So this is actually just a little bit better than twice as grippy as the other one. So for my money, I would want the phone case that has better grip so that it's less likely my phone will just randomly start sliding off of surfaces. So the most important conceptual thing here is that you understand that how we rotated our coordinate axes, and the fact that we had sort of a weird weight force acting. One of them was acting along our incline, and the other one was acting opposite the normal force. As far as questions like this, there's only two ways you can ask a question about this. One is, given the angle, what's mu? The other way is, given mu, what angle will it start to slide at? So you may see a question, for example, about like a car on a snowy road, and here's the coefficient of friction. At what angle will it begin to slide? Which is kind of terrifying if you live in a place like San Francisco. Just a little bit of fun. I found this a couple years back. The street that claims to be the steepest street in the world rises about 30 feet for every 100 feet it goes sideways. If you do the math on that, that's about a 17-degree angle. And so can you imagine living in a place like this? Look how steep this is. If you actually do the math, what we can do is figure out, could I actually park my car here? And the answer is yes, you could. I looked up some coefficients of friction, and it's around 0.9 for dry tires on a dry road. So if you do the math on that, you can park up to about 42 degrees, which is much steeper than the steepest. But on the steepest street in the world, Baldwin Street in New Zealand, it's about 17 degrees. It's only for about 900 feet that it's that long, but still it's very, very steep. The coefficient of static friction using the equation that we just looked at is about 0.31. What's interesting is it varies by textbook and by different authors and stuff, but most textbooks estimate that snow, the coefficient of static friction, is between 0.05 and 0.1. If you compare those two numbers, that means that you couldn't park on this street if it snowed. It's very likely also that you couldn't even walk up this street if it was snowing. So I just thought that was a little bit of fun and application of our really great formula.